Okay, welcome to my third and final part to my cosmology lecture. This is for Cabrillo College, Astro 4, and this is our chapter 23 from the text. But actually I put this together myself without really much reference to the textbook because I don't really need the textbook for this. I know this stuff pretty well. Okay, so where we left off last time was the universe looked like it was at critical density, and so we talked about how that is favored. Our favored theoretical notion for the universe should be critical density, because that is a universe that has exactly zero total energy. Maybe I should pause on that for a moment. You might say, what? Zero? This is not zero, Rick. You would actually, well, in some sense, no, it's not zero, but it is zero in the mathematical sense, because it turns out that to have our most favored, most convenient of all physical principles, the conservation of energy, that in local or even cosmic context, you need to include the gravitational potential energy as a negative. Okay, so gravitational energy is an attractive force that actually provides a negative, so that you can convert that into a equivalent positive energy, like kinetic energy, as it gives up potential energy, and therefore energy is conserved in that kind of a system. You drop something and it speeds up, so where does it get all that energy? Well, in order to have conservation of energy, it must have already had that energy. It just had it in so-called potential energy form. So this is something we already talked about in chapter 4 and 5, but I thought it was worth restating now. So if you have a universe that is expanding but also self-gravitating, and if it's exactly at the critical density, then those two energies are in balance, and actually the universe has zero total energy. We know how to create such a universe out of nothing, just by using the laws of quantum mechanics. So we've always favored, at least theoretically, or hoped, or I don't want to sound like we're cooking the answer before we know what it is. We've just always had kind of a we've always been rooting for a zero energy universe, or at least many of us. I suppose it would be even more interesting if it turned out not to be, and then we'd have more mysteries. But those mysteries would really, those mysteries are almost more mysteries than we want to deal with at the moment. We've got enough mysteries. We still want to know what the dark matter is. We want to know really what the dark energy is. So we've got enough mysteries. Frankly, most people, when we saw that the universe was at zero density, were somewhat pleased, that we live in a universe that obeys the kind of simplicity that, is beautiful. And physics has been very good at finding answers that turn out to be right by following our sense of beauty. Okay, so we're ready to move on. This is the slide that we looked at last time, so let's move on. Now, we saw our first map of the cosmic background radiation, and it looked pretty smooth, except there was a clear bipolar or dipole field to it, which we accounted for by simply the fact that the Sun and the Earth, too, are moving relative to the entire observable universe. And that's because it just so happens, by random chance, that we have a lot of galaxy clusters and superclusters more on one side of the sky than on the other side. And that has acted over time to slowly accelerate us up to about 600 kilometers a second relative to the universe, well, the observable universe as a whole. Okay, but now we're going to ask a different question, and that is, are there any other fluctuations in the temperature of the microwave background on a much finer scale? So what we did is there we go. So we launched a new satellite mission, much better technology, and it's called the WMAP, the Wilkinson Microwave Anisotropy what was the P? Probe, that was it. WMAP, okay, so it rolls off the tongue nicely. And this is what it saw. So all this fine scale gray structure that you see, this is all due to the small scale fluctuations in the temperature. And I hope you can see that they exist on really on all scales as near as you can tell. Now forget about the red. The red is just foreground microwave emission from interstellar clouds and giant molecular clouds that we talked about before. So those are still there, and those still have to be removed. Removing those from the data is challenging, but it's doable. And so they're clearly identified, and they are pulled out. Pulled out at least figuratively. They've been left in on the map, but they're different colors. So what we want you to focus on is just the gray. And you can see some large areas of gray that are a little darker, and you see some large areas of gray that are a little lighter. And you also see medium scale things that are larger, that are brighter, and some that are dimmer, and those very fine scale things that are brighter and dimmer. So it looks like there is structure, there is lumps in the microwave background which would correspond to lumps in the matter distribution on all scales that we can see on this map. Let's take a look again. Let's look at an all-scale, all-sky map, and now we're going to color code it to make it all a little more obvious, and I think you can see that there's lumpiness on all scales. Pretty big scales, and also pretty small scales, about the limit that this satellite technology could detect. So let's take another look just to... trying to take a sphere and flatten it out is kind of challenging, so here's another way that might be a little more intuitive. Let's go ahead and let it be a sphere, so there's no distortions now in how you lay it flat. We're not going to lay it flat, we're just going to photograph the two sides of the sphere, and so you get a 3D kind of impression looking at this. And again, though, the result's the same. You see structure on all scales. Now what you can do is you can ask, okay, how strong are the fluctuations, and on what scale? So 90 degrees, well, that's a quarter of the whole sky. That's the biggest scale you could hope to have any data on. 0.15 degrees, well, that's tiny. That's about the size of, a lunar Maria as seen by your eye. It's barely at the resolution limit of the naked eye. Okay, so that's pretty small. And what you see here is a curve, and the curve has lots of wiggles in it because of what we call acoustic vibrations, acoustic oscillations, that I don't really want to spend a lot of time trying to explain because it's a little too wonky. But I will say just that the prediction of inflation, which we have introduced now, the predictions of inflation follow the simplest model of inflation. Okay, you can cook up all kinds of more complicated models that have less beauty to them. They're not as simple. That would be different. But the simplest model of inflation, which has just one free parameter, obeys pretty darn well the data. Now the data still has these error bars. You can see the size of the error bars is. So it looks like, maybe we could do better. Maybe we could do better. So we designed and then we launched another mission called the Planck Mission, and it had even better quality data. So I like this slide because it shows, first of all, the satellites themselves. They all look pretty different. And the technology, so the Planck Mission was launched in the late 1990s, I think. And WMAP was more like the early 90s, and the COBE was 1980s. Designed in the very early 80s. So COBE, you couldn't see any of the small-scale structure. The technology just wasn't good enough. But WMAP did, and Planck sees it much better. So here, this little man-like figure here, without a head, or maybe he's got a head, looks pretty fuzzy. Here, it breaks up into a lot of smaller scale features. So the Planck mission was a definite improvement. And now let's compare that again to the fluctuations And now we're going to put fluctuations in terms of temperature here. And this is in micro millionths of a degree Kelvin. Temperature fluctuations, this is squared per, and it's microkelvins squared. The reason is because they go positive and negative, and we want to square them so they're all positive, and so it just plots a little better. You could plot it in different ways. But look at this. The error bars are still here, but you can't see them. The error bars are so tiny on these large scales because there is such a large sample. There's so many bits of this all-sky picture that are as large as 0.2 degrees across. That's pretty tiny. Remember, the moon's about a half a degree across. That's about right here. How many full moons would it take to paper the whole sky? Well, a decent number of them. And so there's pretty good data, and so the error bars are so tiny that you can't even see them. And it fits perfectly. I mean, this kind of data just brought all kinds of delight to the cosmology people who designed and executed this mission, and then compared it with the simplest models of inflation. Now you might say, well, what about over here, Rick? The error bars now get pretty darn big, and even the inflation predictions get pretty darn big. So the uncertainties there get pretty big. So what's that about? Well, what that's about is it depends entirely on what we call cosmic variance. So it depends on where are we in the universe. How many 90-degree across blotches of area are there across the sky? Well, about, not many, like 4 pi. Not 4 pi, less than 4 pi. Anyway, there's just a small handful of them. So of course you're going to have uncertainties, and those uncertainties cannot be removed. They cannot be removed, ever. We are where we are in the universe, and that's the way it is, and that's the way it'll always be. So this is so-called cosmic variance, and these error bars cannot be reduced, and even the error bars in the inflationary predictions themselves can't be removed, again, because there's just too few. Because we're at a given place and the universe is lumpy on all scales, even very big scales, and we can't reduce that. Okay, we can't just, if we could move ourselves around magically throughout the entire universe, not just the observable universe, but all of it, then you could hope to beat these down, and maybe they would follow the blue curve here. Certainly looks like it would. Look at how good that agreement is. That is just stunning. So after the Planck mission, the amount of the energy density, matter energy density of the universe in the 3 main components shifted around a little bit, not a whole lot, but a little bit. So now it looks like in terms of dark matter, we have just a little less than 27%. The ordinary matter, what we used to think in the old days was everything there was, all the stuff that makes up stars, you and me, planets, interstellar clouds, all that stuff, that's 5%. A tad less than 5%. And the dark energy is almost everything else, over 68%. So here's lumpiness in the universe. On rather small scales, 10 million light years, that's about the size of a pretty rich cluster of galaxies, pretty big cluster of galaxies. Then the lumpiness is, clusters of galaxies are lumpy. They're pretty obvious on the sky. But when you get to bigger and bigger scales, now 100 million light years, now 1,000, that's a billion light years. Now you're talking about, a tenth of the size of the observable universe. And the universe gets smoother and smoother. And look at how smooth. I mean, this is a log scale. So density fluctuations from example to example damp out. And so on the largest of all scales, we still think the universe is very, very smooth. But cosmic variance means that there's still some lumpiness on even the scales that we could see, and so there's big error bars here. But on small scales, it's pretty darn tiny, and it agrees pretty well. Okay? So the conclusion is that the density parameter, which we often designate with the Greek letter omega, of the universe is 1.0. So what is omega? Omega is just the density of the universe in terms of matter and energy divided by the critical density. So to say it's 1.0 is to say that we're at critical density. That's exactly what is predicted by inflation. The spectrum of the strengths of the density fluctuations is a power law with a slope of -1 in real space. And that's also what's predicted by inflation. Now there's a small little break in that that's due to the fact that there is a preferred scale in the universe. It has to do with the Planck distance. But let's forget that for the moment. This is forgetting about that for the moment. It's a tiny little thing. Let's not obsess over it. The slope has the right slope, okay, predicted by inflation. The acoustic peaks in the WMAP and the Planck power spectrum follows all the wiggles predicted by inflation. It follows them perfectly. So it's looking like inflation, and in its simplest form. I mean, that's what we really like. We don't need to cook up some artificial, kludgy, version of inflation, because then it looks like you're just cooking the books to try and make it look right. It doesn't have that clean feeling to it. You'd like to think that you don't have to contrive. That's the word we used back in Chapter 0 when we talked about scientific method. So we don't want to feel like we have to contrive things to try and make them agree. So when inflation in its simplest form with only one free parameter agrees with everything we see, we feel that, wow, I think this is actually right. Now, some philosophers get all bent out of shape about, well, you haven't proved it. The problem is that I don't think they understand the difference between the idea of proof in a closed logical system like mathematics and in a very open system like the nature of the universe. So I'm going to rephrase something that we talked about in Chapter 0, and that is, in a closed system, yes, you can do proofs because you define the system. You define the axioms, you define everything within it. And within that, then yes, absolute logic is closed, and so it is possible to do proofs and disproofs if you're clever enough. But the universe was not made for us, by us. We wake up one day when we're 2 years old and we look around and there's a universe outside of our skin, and it's up to us to just make sense of it. Okay? And I'm totally comfortable with that, and most good scientists are totally comfortable with it. It's the darn philosophers who get in the way. I will tell you that those in science that I know, and myself included, we frankly disregard just about everything that the so-called philosophers of science, a very highfalutin term for people who I think are out of their depth. They don't know what they're really dealing with. And when you're talking about the real universe, it's perfectly acceptable and it's perfectly correct that there should be some remaining uncertainty. Okay? We don't have infinite technology. We don't have infinite time to figure everything out. There's going to be remaining uncertainties. So, anyway, that was a little diversion. I'm going to pick things up again here. So, why is it that inflation happened? So, a leading contender is the idea of symmetry breaking. So here's, and this is maybe the simplest one to try and make a little sense of for beginning students. The four forces of nature. Four? Why four? Seems like an odd number. Why not one? One seems more natural. Could the forces of nature really be unified if we just look carefully enough? If we just look at high enough energies, when all of the forces could possibly have been unified into a single force? It's kind of a beautiful idea. We don't know whether it's true, but it's at least an interesting idea that actually has borne a little bit of fruit already so far. So we do have some progress here. It turns out that the weak force and electromagnetism, so this is obviously one of the two really weak forces in nature, and then the electromagnetism is one of the two really strong forces in nature. And it turns out that these two forces were unified at an early moment in the universe when it was less than 1/1,000,000th of a second old. The temperature was so high, the energy was so high, that in fact the weak force and the electromagnetic force could be unified and described by a single force called now the electroweak force. And the predictions of that are the W and Z bosons, which have been found in particle physics experiments. Those are at low enough energy, they're not that low, but they're at low enough energy that they are accessible by our highest powered particle colliders, trying to smash things together at high enough energy that, according to the laws of quantum mechanics, just about anything that is accessible at those masses should be produced. And if you look long enough and hard enough and you run your experiment long enough, you should see them. And indeed we do. So we now believe the electroweak force really was a single force that then split into the electromagnetic force and into the weak force after a trillionth of a second. Okay, so that's encouraging. Well, maybe we could unify the strong force into that as well. Unfortunately, that would take a particle accelerator so far beyond anything either financially or technologically possible that we're not going to be able to do it. The only hope that you might be able to come up with something like that is through pure logic, and maybe to look for extremely high energy places in the universe, like maybe the black hole at the center of our galaxy, or or hypothesized primordial black holes in the early universe, to have done the experiments for us and to look for something like that. But the prediction, one generic prediction of a so-called grand unified force, the simplest grand unified forces predict that the proton should not be stable. It should have a finite lifetime, in the same way that the neutron all by itself has a finite lifetime. Neutrons, when you take them out of the nice, comforting, stable, cozy little places that they occupy inside the nuclei of atoms, if you take them out and you leave them all by themselves, they can't handle it. They cannot handle it. And after 11 minutes on average, they just fly apart into a proton and an electron. Electrons, we believe, are totally stable. Protons, we had always thought, well, maybe they're stable, but then with the grand unified theories which were being devised early on, the prediction was that the proton should decay after about 10 to the plus 32, 10 to the plus 32 years. And I think I talked about this earlier as well. Well, how could you possibly test anything like that? The universe is only 10 to the 10th years old, Rick. 10 to the 32 years, that's a long time to wait. But since it's a quantum process, it's really only a probability per unit time, and therefore all you really need to do is to get 10 to the 32 protons all together inside a detector that could detect whether any single one of them decays. 10 to the 32 protons, you can do the math. Turns out that's actually an accessible amount of stuff. It's big, it's many, many tons, but it's not unachievable, and we've achieved it. So in the Sudbury neutrino detector, it turns out there's enough water that we can actually access, that there's enough protons in there that we can test that. And in fact, we see that the proton is indeed stable. In fact, it's stable to at least 10 to the 34, and maybe they're even starting to push it up to 10 to the 35 years. I don't know what the current limit is. 10 to the 34th, I think that number is a few years old now, so they might have been able to get that up a little bit higher. So that's 100 times longer than the simplest grand unified theories. So we don't have a grand unified theory of physics yet. But if we did, at least in general outline, it might look something like this in terms of the evolution of the universe. So you start out at the Big Bang, and maybe there was one single force. We'll call it the Force. Why not? Everybody loves Star Trek. Star Wars. Not Star Trek. I guess we love Star Trek too, but Star Wars, yes. Obi-Wan Kenobi, the Force. May the Force be with you. At 10 to the minus 43 seconds, the temperature is 10 to the 32 Kelvin. Particle energies that are being created and destroyed at these kind of temperatures are 10 to the 19th billion electron volts. As the universe expands and cools, it follows this track, and then gravity would separate out. That's at least the idea, maybe. None of this is proved. It's speculative. It's sort of beautiful in a way, but it's uncheckable. The only thing we know for sure that actually happens is down here after a trillionth of a second. So the electroweak and the electromagnetic split to the weak and electromagnetic forces, that we got confirmed. But we don't have this yet, the strong force, and then gravity coming out. The gravity is an extremely weak force, and it separating out from this probably would not have been a big deal in terms of energy in the universe. However, this split, which would happen at a time around 10 to the minus 33 seconds or so, that would be a big deal because this is the strong nuclear force. That is a very strong force. And that's electromagnetism, and that is a very strong force. These are comparable in strength. They only differ by about a factor of 100 in strength. Okay? So that would be a big deal, and that could have added enough energy to space to have generated inflation. A negative gravity to space and generated inflation. At least that's a possibility. Okay? So gravity would freeze out first, but it's the weakest force and therefore would not be a big deal. Then the strong force would freeze out of the so-called grand unified force. And that separates the strong and electromagnetic forces. Those are the two big forces in nature. The energy liberated by these two could perhaps have powered the inflationary epoch. There's other ideas, even wilder and more speculative so far. Inflation is bizarre, but actually it's a totally logical outcome of well-tested quantum physics, and it's passed its first tests. Again, the simplest model of inflation is the one that works the best. I thought I'd throw this slide in just for fun. Is there any more freezing out in our future? After all, we got 4 forces. Maybe we'll have 5 if we have another symmetry breaking. The long-sought Higgs particle is the last piece of the standard model of particle physics. It was discovered about 8 years ago now. The Higgs gives rise to the property that we call mass. It's a quantized Higgs field particle. It's pretty heavy, 126 billion electron volts. That's pretty heavy. Took a long time, a lot of data before the LHC, the Large Hadron Collider, could by random chance have accessed energies that big and have maybe seen Higgs particle, and finally after a while the data added up enough and yep, there it is. But the fact that it's not infinite, or some other value, let's not go off to the wild blue yonder here, may mean the universe is in a false vacuum. It is not yet at the actual true vacuum, the bottommost energy state that the universe could be in. And after all, we do still have a cosmological constant that's an energy density to space itself. So this particular mass is very close to the critical mass whereby in the distant future, when the expansion has cooled sufficiently further, we're already at about 3 degrees Kelvin, but if we go down much, much lower still, we may spontaneously transition to a true vacuum state. And in the process, we would have another inflationary kind of situation, and the forces would all change, and we would just destroy everything at the speed of light. So that would be a massive bummer. But it's still a prospect that's extremely speculative, so I don't know anybody who's actually worried about it. I don't even know of a whole lot of work that's still going into that, but there's probably some people still thinking about it. Don't lose any sleep over it. And you know what? If it happens, you'd never know it anyway, because it goes at the speed of light. So it wouldn't be like in the movies with screaming people and all that. Okay, well that's a picture of the control room, one of the control rooms in the Large Hadron Collider, I think. Actually, you know what? I'm not sure which collider this is, but anyway, it's one of the big particle colliders. When you look at data from those, then what you're basically seeing is the tracks made through space by the particles that are created by collisions. and you look for collisions, and then you look for the particles that are generated by the energy of those collisions. If they have charge, then they follow curved paths. If they don't have charge, why do they follow curved paths? Because there's very strong magnets nearby, and charged particles moving through a magnetic field, as we talked about, they create curvature. And if they don't, then they would be uncharged. So that's an easy way to tell whether your particles are charged or not. And it looks a lot like fireworks. Now, if you're a real particle physicist, you might look at this and say, wait a minute, Rick, this does... And, okay, you know what? It's a cheat. I admit. I cheated. This really is fireworks. Sorry. It was... I liked it. It's got color. It's... Anyway. Real particle tracks do sort of look kind of like that. Okay, here's cosmic history back to the first 3 minutes. Okay, back to the first 3 minutes, we have very high confidence that we understand what's going on. Very accessible to the laws of physics that are easily demonstratable in our technology that we have, mastered very well. So today we live in a time with a lumpy universe with stars and galaxies. You go back earlier, the galaxies are denser. Back far enough, earlier, way earlier than the first billion years, then galaxies haven't really formed yet. You just have stars, and then even the stars haven't formed, and if you go back to 300,000 years, it's just hot gas. This is where the microwave anisotropy is visible. The lumps formed in the early universe by the dark matter that we decided is cold dark matter. It must be cold dark matter to have the lumpiness that we see. Then if you go back even earlier, then you're in the era of not atoms but nuclei, and even into the quarks that make up some of the nuclei, and they don't make up electrons, but they make up they make up some of the particles. And you can even have nuclear fusion going on, and if you go back even earlier, well then things get even more different. So you go back even earlier, now this is the so-called particle era, earlier than the first thousandth of a second, back to the 10 billionth of a second. So particles exist here. And then you go back further, and you're in the electroweak era, so you have now unified two of the four forces of nature. And then maybe you go back to the gut era, the grand unified theory, which we don't have yet, but we think, or we hope, might still be out there. And then if you go back far enough, the universe is so hot, the travel time from causally connected places gets so small, you're actually in the total realm of quantum, you're back to even before, you're back to a size where the universe is fuzzy even on that scale. And we call that the Planck era. And before that, all of these things cease to have meaning. Okay, you can't talk about photons and particles and anything. At the Planck era, everything dissolves into a quantum fuzz. Now, I think we talked about this before, but this is probably a good time to again try and explain to you where the matter lumps that we see in the cosmic background, where they came from. So the universe really did start, we think, in a quantum state. And that means that the density from place to place to place was not really truly constant, even though nominally it's constant. But because of quantum mechanics, it's only a constant plus or minus this fuzz factor of quantum uncertainty. And so in a very real sense, the density from place to place and moment to moment changes by the amounts allowed by quantum uncertainty principle. Now, as you expand from that, you transition out of the time when you are at the quantum realm into a realm where you're large enough that whatever lumps are still there at that moment, they have now frozen in. This is still very, very, very early, but it's out of the quantum realm now, and forever after, those lumps are frozen in. Now, those lumps were only on the size of the quantum uncertainty principle, way down in the subatomic realm, but now they have been blown up by inflation to finally be galaxy-sized fluctuations in density. And again, those fluctuations are just a reflection of the quantum uncertainty principle. They're literal quantum uncertainty fluctuations frozen in and then expanded to scales big enough that is now frozen into the stuff that came out of the Big Bang itself. Now the particles that make up matter are charged and feel the electromagnetic and strong forces, and they're way too hot to fall into lumps at this point. But the dark matter doesn't feel any of that. It feels maybe the weak force and nothing else. Not electromagnetism, not the strong force. So the lumps in the dark matter could form right away. And it's the lumps in the dark matter that the gas of hot particles and hydrogen and helium gradually then fell into. Now, after 300,000 years, not much had fallen in. It was still pretty darn hot. But it had fallen in a little bit, and so there is lumpiness in the ordinary matter due to the stronger lumpiness in the dark matter, because the dark matter lumps could form right away, right after the quantum realm. So the lumpiness in the ordinary matter is only about 1 part in 100,000. I mean, it's really, really, really smooth. I mean, it makes homogenized milk look way lumpier by comparison. So when I say lumpy, I don't want your imagination to run off with you. It's really smooth, but it is lumpy to 1 part in 100,000. So that's a little teeny bit of lumpiness. Okay, so here's another way to try and map out the history of the universe. Dark matter produces the density wrinkles, and then eventually the stable particles are produced, and then those eventually fall in, produce little teeny tiny lumps. Those are visible in the cosmic microwave background, and then after 1 billion years or so, you get lumpiness big enough to start forming the stars, and then they fall together with the gas around them to make the dark matter and light matter formed giant black holes in the middles of galaxies, and then more stuff falls in around it, and you make disks of galaxies, and you make halos, and eventually you're here, where we are. There's us. Okay, there's your short history of the universe. Here's another history. So you can plot it in terms of time. Now, this is a pretty dramatic log scale, so we're going to go from 10 to the 20th seconds, that's about now. 10 to the 19th seconds or so is now. One with 19 zeros after it, that's a lot of seconds, about 13.7 billion years. And you go back, and of course you don't have to go very far before you're already at the first second of the universe. There's the first second. Everything back here is the first second. Now, we think we know physics pretty well to get back to around here. And even, the weak and electroweak force, we think we understand that. So we got it nailed, we think, pretty well back to about here, 10 to the minus 12 seconds. Going back further, it gets pretty fuzzy. Okay, not just because of quantum fuzziness, but, knowledge fuzziness. We can't probe physics at scales that are this energetic with the equipment that we can afford. Okay, we can't make particle accelerators that can probe down here. So we're left with our smarts and our sense of beauty, and then trying to find maybe out there in the universe itself is the only place where these kind of experiments have been run, and so people are trying to be very clever. This is, in fact, is an idea probably worth mentioning, and that is that, there was a time back when I was a kid where particle physics people worried about the very small, and cosmology people worried about the very big. And those two didn't have a whole lot to say to each other. But they've gotten much more cozy together, because the particle physics people realize that they've now understood enough that if they're going to get more answers, the only place where it's been done is in the universe itself. And so they're going to have to talk to their cosmology people. And of course we have cosmology people who maybe even came from particle physics backgrounds, and we have cosmology people who have learned particle physics very, very well. So I'm thinking of my old compadre Joel Premack, and another compadre Stefano Profumo, who are in that category. Particle physics people who are very good at understanding cosmology and trying to synthesize the two together. Those are the kind of people who are really going to get this figured out if we ever get it figured out. I think. Okay, here's another little mystery that we can ponder. So in the beginning we had high enough energy that you could actually create out of the photons, the pure energy of the early universe that was floating around, the photons, way more powerful than your typical gamma rays. Powerful enough that out of that you could create particle-antiparticle pairs. So according to quantum mechanics, as long as you obey energy conservation, matter can turn into pure energy by combining matter and antimatter. Anybody who's watched Star Trek knows that. Okay? But the process can also be run backwards, and so you can have pure energy turn into particle-antiparticle pairs. So you can have photons that are powerful enough turn spontaneously, all by themselves, without any encouragement from outside, turn into an electron-anti-electron pair. Now, how long will that last? Well, electrons and anti-electrons are oppositely charged, and therefore they will attract each other. And when they attract each other and merge, then they're going to produce pure energy, in other words, another photon. So it's really a soup of particle-antiparticle pairs that are being created and then destroyed by their own recombination over and over and over. That's the earliest universe. And you've got electron-anti-electron pairs, and then at an earlier time it's hot enough that you can actually produce that you'll have photons that are powerful enough they can actually produce proton and anti-proton pairs, and those are 2,000 times more powerful, roughly 1,860 times more massive, and so it takes 1,860 times more energy to produce those. And if you go back further, you can produce even heavier particles and antiparticles. Now, as the universe, let's go forwards in time now again, and the universe goes forwards in time, and then the matter and the antimatter, of course, they run into each other and annihilate, and then they want to perhaps have those photons split again. But you know what? If the universe is expanding, it is cooling. It is stretching out those photons. Those photons are becoming less energetic. More of the energy of the universe is going into its expansion, and less of it remains in the form of its photons wandering around. And a point comes where those photons are low enough energy that they can't produce protons and antiproton pairs. Then, whatever proton-antiproton pairs are out there, sooner or later they're going to find each other. Sooner, actually, rather than later, because they're oppositely charged, and boom, they're going to turn into a photon, and then that photon's not going to be able to go back into being a proton-antiproton pair. And eventually that's true also of the electron-anti-electron pairs, and that's about the lightest particle there is, except for the neutrino. And so you ought to expect that, well, at least the simplest universe you would imagine would be one where there's exact perfect balance between matter and antimatter in this early universe. And therefore, as the universe cools, you should end up with no matter and no antimatter. It should all just be photons. All photons. Just photons. Spreading out. Following the Hubble expansion. Well, of course, that's not what we got. That's not what we see. So there's got to be a slight imbalance in these processes. A symmetry that is not perfectly obeyed, but pretty close. Because we do have matter left over, and we don't have any antimatter left over. Whatever antimatter is produced locally, recently, and doesn't last very long before it finds an antiparticle partner to run into and smash into and then disappear. So antimatter is an unbelievably extremely tiny fraction of the matter in the universe today. So we have an imbalance. It's not very much. Only 1 part per billion. So that's another way of describing how many photons there are of the cosmic background radiation compared to the number of particles of matter. There's about 1 billion photons out there, and most of the photons out there are cosmic background photons. There's about 1 billion of them for every individual particle of matter. Every electron, every proton, every, I'm trying to think of stable particles. that's out there. Okay, so that's pretty good, but not perfect. Why is there an imbalance? Well, at least we know that there are other symmetry, there are other broken symmetries in the laws of physics, and so it doesn't amaze us that there might be an imbalance here. Clearly, physics is not totally done. Even the standard model is perfectly as it's obeyed. We don't have an answer for this imbalance. There's still new physics to be learned. So I'll leave that as a mystery because I can't tell you the answer. We don't know the answer. Well, let's summarize. Okay, so this is the last slide of any content. Inflation not only has solid observational support, it's very difficult to see how any mechanism generating inflation doesn't just have to be the splitting of the four forces of nature, but we can't think of any mechanism that could generate inflation that would not also produce a near infinite number of universes. So we're going to talk about that in more detail with the next and final chapter that we're going to go over this coming week. And that, strangely enough, is the chapter on life. So the early parts of that, we're going to talk about why it turns out that eternal inflation also provides a natural explanation for why we have a living universe. In fact, if there really is one and only one universe in the whole of all existence, it's very, very hard to see why this one would be so lucky in the chosen 20 free parameters that describe the standard model of particle physics. Why those 20 free parameters would just happen to work out to support the ability for complexity to develop. It's way easier to go wrong. There's very few universes that if you just cook up those 20 free parameters randomly, you're going to get anything except maybe black holes that emerge instantly, and black holes are very, very simple things, or just particles flying apart that never collapse. You need stuff collapsing on big scales to support environments that are stable enough to permit the evolution of complexity. And there's a lot of ways to go wrong. And anyway, we'll talk about that more in the next lecture. I won't do it all now for you. But eternal inflation solves a problem that otherwise doesn't seem to have a solution. A solution which is other than religious. Okay, so you can just say, well, God did it. Not very satisfying. Okay, to come up with a supernatural being who just has every Swiss Army knife you could imagine, and yet who isn't also complex. It actually defies a reasonable look. But I'm not going to go into that either. That would take me too far afield. All right, so we're almost at the end. Here's our red slide. There's our summary for cosmology. Of course, there's way more that can be said on cosmology. If you want to learn more, I'd highly recommend the YouTube videos from Lawrence Krauss. He's done some really great stuff there. And Sean Carroll has also got some great stuff. And it's good to see, and it's on levels that Cabrillo undergraduate students could understand. And it's always good to be challenged a little bit. You want to be stretched. Stretched is growth. Growth in knowledge is a good thing. And once you start doing that, of course, YouTube's going to come up with all kinds of other YouTubes that are on the right side of your screen and that you can click on also. And so there's just so much great stuff out there. But this is enough for us right now. And let's see if there's any more that I want to tell you. I think there might be, because you're going to be quizzed on this someday. Comes our final exam, we'll have quiz 6, which will cover cosmology as well. So summarizing some of our cosmology, we learned there's dark energy, and the evidence for dark energy is that white dwarf supernovae are dimmer than expected in distant galaxies. And that means they have expanded away, farther away than we would have thought, given the recession velocities that we measure. So that's telling us that the universe is actually accelerating its expansion. Okay? White dwarf supernovae, type 1a supernovae, are dimmer than we would expect. Okay? So during the first few minutes after the Big Bang, there was hope early on, I mean like 60, 70, 80 years ago, that maybe nuclear fusion reactions would have made everything, all the 92 chemical elements, but we actually did the detailed calculations and realized that no, we couldn't, because we couldn't get around the lithium-beryllium roadblock. By the time there was enough helium around that you could try and maybe make some carbon out of it, the way stars do, the density was already too low to get them together. Remember, to make carbon you need 3 heliums to all run into each other at the same instant in order to make carbon. And so the universe itself could not do that. Stars can do that because they're very dense and they're very hot and they stay that way for a long time. The universe did not stay that way for a long time. It expanded too quickly, and so that didn't work. So yeah, you need to remember that. By the time there was enough helium around, the density was too low. Okay, now another question you might ponder is, when we look out 14 billion light years, are we seeing the entire universe? And I hope you realize now the answer is no. We're only seeing the observable universe. We're only seeing what has had a chance for light to get to us. And light has not had a chance to get to us from farther away than that, because it's moving away from us now faster than the speed of light. So no matter how fast it tries to travel, of course it's only going to be able to go at the speed of light. So no, it does not encompass the entire universe. The entire universe that obeys our laws of physics, I'm not talking about the multiverse, I'm talking about just our individual instantation of the multiverse, our individual universe. Even that is probably infinite or almost infinite. It's certainly bigger than we can see by a factor of 10 to the 90th or some huge number, which keeps changing as we get better data. When did radiation first travel freely for long distances without interaction with matter? Well, that was when the protons and the electrons were first able to combine, because they were moving slowly enough now. The temperature was cooler than 3,000 degrees. So when the protons and electrons first combined to form atoms of hydrogen, that's when the microwave background photons were then free to travel. Because remember, hydrogen is most of the universe, and of course the same is true of helium. They would be free to combine by then as well. So neutral atoms can only absorb photons if they have the magic wavelengths, and if they're charged particles, though, they interact with any photon, and so the universe is opaque. Okay, so now let's do a little imagination. Suppose you instantly, magically take yourself out to the very stuff that is the cosmic microwave background. Okay? So you identify a little patch and you say, that's a lump. I think that lump's going to turn into a galaxy with stars and planets and people on the planets, and I'm going to just instantly transform myself and be one of those people. Okay? Now, you're there. And now you're looking back towards us. What will you see? Will you see a Milky Way galaxy with spiral arms and all that? No. The light of the present Milky Way with all that structure hasn't had a chance to get to you yet. You're going to see our Milky Way galaxy as it was 13.7 billion years ago, and back then it was just 3,000 degree hot gas too. You're just going to see cosmic background radiation. So everybody in the universe sees the same thing. It's just made of different stuff. The names you would attach to individual particles are different, but the laws of physics are the same. And so everybody, everywhere, sees the same thing within this entire universe, vastly bigger than the observable universe that we can actually see. Okay? So we, in the Milky Way, to you now at that edge, you would just see us as microwave background. Worth remembering. Okay? So, now, summarize what is the favored cosmological model. The favored cosmological model is a universe that is at critical density. So I hope you got that. If you got nothing else out of that chapter, I hope you got that. And the mass energy density is dominated not by matter, not even by dark matter, but by dark energy. Something even a little more mysterious. So our universe is dominated by dark energy already. Again, it's about 68% of all the matter energy that there is. And then if we go back to the beginning of the chapter, remember we talked about Olber's paradox. So Olber's paradox was if you just start with the simplest of all universes, one which is just infinitely peppered with stars, and they've lasted forever, because if you want a simple universe, why have a beginning? That's not as simple as a universe that's infinite in time. Infinite in time, infinite in space. Okay? Then the prediction is you should see a night sky that's as bright as the surface of a star. Since we don't see that, that means the universe imagined by Newton and Olbers could not exist. There had to be a beginning, or there had to be an edge to space. Now, it's true you can refine that prediction by putting in the expansion, which redshifts the light over a finite realm. But in fact, we do know now that the universe does look like it had a beginning. And what is the curvature of our universe? So to say that we have a critical density universe is also to say that the curvature of the universe is zero. We live in an overall flat universe. It's kind of like a table that's been sanded but not sanded very well, and so it's got lumps in it. You know, if you run your hand over it, there's lumps, there's hills, and there's little valleys, and not very much, but they're there. Light would follow paths like that, but if you make that table infinitely big, it would still be a, quote, flat table. So yes, light doesn't really travel in straight lines. It does follow little curvy paths as it goes through regions of higher and lower density, but the overall path of the light is, quote, flat. It's really a two-dimensional term, and you have to extend it to a three-dimensional universe because we have 3 dimensions of space. But it gets across the point. Okay? So they're like straight lines, but they're not drawn very straight because there is lumpiness in the universe, and that affects how gravity makes things curve, as we talked about. There's about 1 billion cosmic microwave background photons for every particle of matter in the universe. So we talked about that today. You should remember that. Okay, it means there was a slight imbalance in the matter-antimatter. 1 billion particles of matter for every 1 billion and one particles of ordinary matter for every 1 billion particles of antimatter in the early moments, when there was still a lot of antimatter around out there. And there was plenty enough energy for the photons to split into particle-antiparticle pairs. Okay. Do the laws of physics as presently understood permit the idea of multiple universes with different forces and different fundamental properties? So we're going to talk about that again more this coming week. But in fact, I've already recorded that. It's already on YouTube. You guys can listen to it whenever you want. And the answer to that is yes. It looks like it actually solves a lot of problems that otherwise don't look like they have easy solutions. And different universes with different laws. We just happen to live in this one, and you rolled the dice, the 20 different dice that determined our universe, its laws, and we came out with what we came out with, and actually turned out pretty lucky. We hit the lottery, we hit the jackpot, because it permits life. And we love life. I mean, we're alive. Okay, anything else I need to make sure you understand? We want to go back into history a little bit, not very far actually. Why was inflation originally attractive? What was so exciting to Alan Guth when he first realized that inflation was actually consistent with the laws of physics that we already knew, and yet it had this fantastic property of huge expansion when you add negative energy to empty space? What was attractive about it is it could explain why the universe would have the same temperature on opposite sides of the sky. And in fact, when you take into account the rate of expansion over the whole universe, even place, you don't even have to go to opposite sides of the sky to have a problem explaining why they're at exactly the same temperature. Even places just a degree or two apart from each other on the sky were still out of causal contact, always. So how'd they know to come to the same temperature? Inflation solved that by saying, but you don't realize the first tiny fraction of a second the universe expanded way more than you thought. And so it came from a way tinier place where the universe actually had plenty enough time. They were close enough for temperatures to equilibrate very well during that tiny fraction of a second. And then got blown out and has now been expanding at the more leisurely rate of the Hubble expansion. Okay, so what's more that I need to tell you? Okay. Boy, it looks like I've covered everything. Well, good. All right, you guys are ready. All right, so I'm going to go ahead and end this, and I'm going to get this uploaded to YouTube tonight. And enjoy Part 3 of Cosmology, Astro 4, Cabrillo College. Thank you, guys.